48 digits total. And one of the innovations in his algorithm was that one of the three integers is much smaller than the other two. So that's sort of the great idea that allows him to find it, whereas previous algorithms failed. Okay, and then Hooley, in a series of works starting in 1995, he showed that so the Ghosh-Sarnak type result is not known for sub-3 cubes, but 42 and another representation of 3. Yeah, so those are yeah.
What year was that?
Also 29.
Okay.
Let's see. Okay, so yeah, so Hooley showed that you can solve this for at least I mean not almost all, but there's some exponent array, so like 0.917 or something. Integers, positive integers b up to a, and this exponent is as a goes to infinity. Okay, and then let's see. So on the other hand, since this is not optimal, we can ask what can we say under like standard conjectures at least. And then Hooley, in a series of 2 works starting from 86, he showed that you know, this for at least a to the 1 minus epsilon integers, b up to a, again as a goes to infinity. So I mean, this epsilon, I guess, sort of begs to be addressed, and this is sort of what Ghosh and Sarnak suggested that okay, so sorry, I forgot to say the hypotheses. This is a conditional result under hypothesis HW, which HW basically stands for Hasse. So he assumed basically, I mean, modularity of certain Hasse functions plus G area. I will sort of explain what exactly, which precise Hasse functions are needed later, but for now, I'll just state it in this form. Okay, and then let's see. Yeah. So okay, so yeah, Ghosh and Sarnak suggested that I look at. I mean, basically, it's not just going to be a single Hasse function. There's going to be a family of Hasse functions that are involved. And because of that, we can try to go further using random matrix theory predictions. Yeah. So basically, the sort of
perhaps you should say that kind of wearing people always make x, y, z positive, and you.
It's essential, yeah. Certainly, 33 cannot be represented as a sum of 3 positive integers, but yeah. So it's very important to allow sort of weird kind of regions in order to get almost anything. I mean, you can already see this in the Ghosh-Sarnak example, Markov type. It's essential to allow not just like, yeah. Okay, so okay, so the result I want to talk about is sort of assumed standard number theory conjectures on L functions. So this will certainly include Hooley's hypotheses. So HW, but also I guess random matrix theory type predictions, which I will state maybe more precisely later. And also some things about unlikely divisors. So what I mean by unlikely is just there's going to be some polynomial later, also a discriminant polynomial, and it should be unlikely for this. What I mean by unlikely is the event of a large prime squared dividing the value of the discriminant. So this is basically the Square-free Sieve Conjecture. So okay, so if you assume these, then 100% Okay, so there will be two results, I guess. One for if you allow all integers positive or negative, and one if you restrict to positive cubes. So 100% of admissible integers are sums of 3 cubes. So in this G of this value set of G, or if you can do it with positive integers, then if you restrict to positive integers, then there's not enough cubes, so all we can say is positive density. And but yeah, so there's some conjecture for the precise density of the, but my methods are not capable of it. Okay, and then a brief remark. So this is like a 100% conditional Hasse principle, I guess. So you might ask, can 100% be replaced with all? And I mean, this is a big open, like a very tantalizing open question. I really don't know, but if you replace sums of 3 cubes with like different coefficients, then the answer is no, you can't. There exist possibilities. And this example is basically due to Hassel's and who gave the first examples of, I guess, the cubic surface that failed the rational Hasse principle, but then you could sort of apply it to study integral Hasse principle. Okay, and another remark is, I mean, in both Hooley's work and in mine, the results are sort of something about, additive number theory problems, but then the hypotheses are kind of different, of a different flavor. They're more multiplicative, stuff about like L functions, divisors. So, okay, so I guess before saying, I guess there will be some more background I need to introduce, but sort of maybe I can give like a brief cryptic overview of the proof. So the idea is, I mean, we're looking at cubic equations in 3 variables, and we're going to look at sort of, there's a standard statistical idea to sort of study this 100% for statistical results by doubling the number of variables. And then if you have these, then there are sort of 3 critical exponents that sort of agree. And okay, so these are all equal to 3, but then in Hooley's work, there were sort of epsilons, I guess. So that's why he got the result only up to an epsilon. So I'm just writing these epsilons for the sort of the number of epsilons around each exponent. So there's sort of 1 source here and then 4 sources here. So there's like 5 total. So the proof sketch is to, I'll explain how to remove like maybe some of the epsilons. We probably won't have time for all. Okay, so, and the rest of this, I mean, this part is sort of what I'll call, I guess, stats 101 and 102, which I know. So, okay, so stats 101.
Wait, so M is the number of variables?
6, right, yeah.
Okay.
And then, yeah, I'll explain, there are 3 exponents that are all the same, and I'll sort of explain where they come from. But of particular interest is this -2 here. It's related to what's called the double coefficient effect. So the 2 there is the double. All right, anyways, so stats 101, yeah, I guess I want to introduce what it sort of, we want to count in sort of 0 or level sets. And basically the sort of minimal generality I need is something like, we can look at these polynomials of the form, a sum of s cubes, where s is either 3 or 6, just to fix ideas. And then we can look at sort of, I'm going to need to look at not just boxes, but also some weirder regions. So let me just call a region nice if it's compact and semi-algebraic. So this is general enough for my needs. And then I'm going to have some scaling parameter for this region x going to infinity. then let n p minus p. So I'm going to phrase this as a, I guess, zero set of p minus b, but it's also, you could of course think of that as a b level set of p. So I'm going to look at the number of points, integral solutions in this x times k, so dilate k by a factor of x, and we're looking at the level set p equals b, which is of course the same as the zero set of p minus b. It's just convenient to use the same notation for both. Okay, so an example is if, I mean, I said, okay, like I need more than boxes, but like throughout this talk, you can just pretend that k is a box. So if k is -1, like this, a unit box, then of course the scalar is just x times k is just going to be the scaled box. And okay, so there's a standard way to, why is this stats 101? Well, there's like a standard way to think about like heuristically what the points are. So we can look at the integral points, all integral points, this total space, the integral points in xk, and then look at their values under p, like we're looking at level 6. So the fibers, okay, well, I mean, every point x in here is going to map to some value p. I mean, p is like a cubic polynomial, right? So it's going to be at most of the order x cubed, since we're restricting to this region xk. And then on the other hand, this has sort of x to the s points roughly total. So so this diagram implies that n, this level set np minus k, np minus b, x is sort of roughly of size x to the s minus 3 on average, and L1 for just the first moment kind of over b, over b plus less than x cubed. So if b is bigger than x cubed, there are no solutions then. Up to x cubed, there should be, at least on average, and first moment it is this. Okay, and then the sort of Hardy Littlewood prediction, which I'll call like a purely randomness prediction. So this takes the form, roughly speaking, it looks something like this count should be some particular constant times x to the s minus 3, which is basically, you should think of it conceptually as a product of local density over all primes and also at the infinite. So it's basically a more refined version of this vibration kind of heuristic. And basically this double approximately sign just means I'm lying a bit in general. So for 3 variables, this singular series is pretty subtle, so I'm not going to get into that. But conceptually, you can think of this as purely randomness prediction. And roughly it looks like x to the s minus 3, but then you need to correct by these local densities that measure how different your equation is from a random one, what sort of local. Okay, so yeah, I guess that is stats 101. So now we can move on to stats 102, which is, I guess I'll call it, so it's basically the idea is double number of variables. Another name you could give it is rags to riches, I guess, because somehow in 3 variables, there are not many solutions, but on average, we can reduce it to something in 6 variables, which has, is supposed to have a lot more solutions. So, okay, so I guess I don't want to keep writing x and y, so I'm going to switch to indices, so y1 cubed plus y2 cubed plus y2 cubed. And then, so I mean, yeah, so I guess we looked at this first moment map kind of like from z to the, you just look at the values of p. But then we can, stats 102 suggests that we also study the second moment of this. So we look at the second moment map. The two fiber product G. And of course, this fiber product, I just mean pairs Y and Z such that their common value is the same. That's what I mean by fiber product. So at each fiber, we're sort of squaring it. Okay, so then, well, G of Y equals G of Z. This can, of course, be rewritten as an equation in 6 variables for a single form f of y, yz equals 0, where f for the rest of this talk will be x1 cubed plus order dot plus x6 cubed. So 6 variables now. Yeah, so basically, what is the point of this? So basically, using the Cauchy-Schwarz inequality, or what probabilists call the second moment method, if you let K be this, I guess, box that I mentioned earlier, then if these point counts are sort of up to a constant, what they should be, what Hardy and Little have predicted, then you can show that a positive density of integers lie in, are some positive so this is like a qualitative kind of thing, but then this sort of begs the question of, I mean, what is the true asymptotic here? Can you say more using it? And this is where Hooley's conjecture comes into play. Basically, the problem is the Hardy-Littlewood conjecture is false for f equals 0, but there's a correction which has significance for these statistical problems. Okay, so in a different paper than the previous one I mentioned, Hooley showed that, okay, so the Hardy-Littlewood prediction, it's purely a randomness kind of prediction, and it misses trivial solutions, such as, I'm not going to explicitly write out the full definition, but basically it's something like you can pair up the variables to get trivial solutions. Like, for example, x1 plus x2 equals x equals x4, and so on to 0. Yeah, so I guess I've explained sort of two of this recursive exponents. Well, there's the number of variables minus the degree, that's the Hardy-Littlewood exponent. And m over 2, that's these trivial solutions. So 6 over 2 equals 3. Okay, but so we have this, I guess, counterexample to Hardy-Littlewood, but you can, there's a Hooley basically conjectured. I'll call this HLH, so Hardy-Littlewood Hooley. So, and I'll state it, I mean, for, I guess, regions slightly more general than what Hooley considered, but anyway, same idea. So for any sort of nice region, K, it predicts an asymptotic where you sort of simply add these two contributions, the randomness and the structure. So C, I guess I'll call this Hardy-Littlewood for the singular series prediction, the randomness prediction, product densities, and then plus the number of trivial solutions, X, up to an error of little, so this is asymptotic, up to an error of little form of X. And this is, of course, as X goes to infinity. This is allowed to depend on F and K, but that's okay. In practice, we'll think of usually K as being fixed one at a time, and then at the very end of the argument, increasing. Okay, and then so this is Okay, so I sort of motivated this as something that we can try to apply it. This is more refined than this upper bound. So we can try to say more about sums of three cubes using under this conjecture at least. And this is precisely what Simona Diaconou did in her senior thesis under Sarnak in 19. But maybe I'll say it in a slightly different form, or maybe slightly for slightly more general reasons. So basically say for all regions, all nice regions, another reason why I mentioned the Ghosh Sarnak result at the beginning on the Markov typesis is variance analysis. Basically, it uses a variance analysis, which I mean, other problems in the Waring type problems have used, but sort of not for the sort of critical problems we're considering. So the ones near the boundary, I guess. I mean, scary term is log Clavials. But anyways, the idea is just the ones that there are the fewest solutions, but we still expect there to be solutions. So there are some ideas that are needed here to push. For example, allowing all nice regions is really important, or allowing enough weird regions is important. Not boxes enough are not enough. Boxes alone are not enough. Okay, so this is. Okay, so that concludes that. I guess maybe what is known towards this HLH conjecture. So what is known towards this?
Why we run out of time?
Yeah, yeah. Okay. Okay, so Hooley, yeah, so I guess I sort of mentioned this earlier, but yeah, so he got a near optimal estimate under
I can do it wherever you want to sit.
under this hypothesis HW that I mentioned earlier. So yeah, basically modularity plus GRH for certain Haskell functions. I guess I still haven't introduced that, but I promise I will soon. But let me just, this is not the main focus of the talk, but I want to just add a remark that since there will be a family of L functions that are not just a single one, so you could ask, do you really need GRH, or can you get away with GRH on average? So let me just say you can, and basically the sort of technically best way to say this is just that, cleanest way to say this is that the large-sieve hypothesis would suffice. This is in the spirit of the Bond-Diary type work. They use a large-sieve for Dirichlet characters. Not going to say anything about this. This large-sieve hypothesis is still very open, but maybe I'll mention that at least if you just wanted the known results by a tiny bit, then there's a different problem that you can do. So there exists unconditional applications of this idea to maybe if you replace one of the cubes with a square, then somehow you can. It's already known that the Hess principle almost always hold. You can like try to reduce the exceptional set. So this allows you to do this. And, so this is basically building on the work of a lot of people. So Gudern sort of carried Hooley's idea over to this problem. And then Duke and Kowalski proved a very general large sieve. It's far from optimal, but it's at least if you just want to win by a tiny bit, then it gives you like GRH, quasi-GRH on average, sort of. And there's also, I mean, there was another ingredient was like modularity, I guess, but in this case, the elliptic L functions are elliptic curve L functions, so by modularity theorem, that's all okay. But this is not really what I want to focus on. I just mentioned. Okay, so like how did, I guess I want to explain like how did Hooley's argument go? So basically, I mean, with a lot of Hooley's work, he's kind of, I guess, doing things before he was supposed to, I guess. So he did not have the delta method available. So maybe I'll explain what the delta method is roughly, then I'll say what Hooley did as a replacement for it. So it's everything goes back to Klosterman's idea in 1926. And the sort of modern form, which sort of removes a lot of the deficiencies in the original Klosterman method, goes to Friedlander. Sort of a cleaner form for the. And what this says is we fix some nice read in X, and then we K, and then we look at these point counts and FKX. Then roughly you'll get something that is like the expected value over this dual variable. I'll explain more where this comes from. Over not x, but now something shorter, x to 1/2. And then another average over sort of modular. This is where the L functions will come into play. And then this double average of this quantity. So in the circle method, you get like incomplete exponential sums. But the point is that these SCNs, which I'll now define, are complete exponential sums. A mod. So it will be a sum. So the 6 variable sum of these exponentials E mod n of A f of x. So there will be, it will not just be A f of x, but there will be sort of it's a Fourier transform. Here, as usual, E of n of t just means e to the 2 pi I t over n. And the prime just means, don't worry about this, prime just means I'm restricting to residues A co-prime. Okay, and then basically I can say what Hooley's shortcut in one line. Basically he had this with, I guess, a less than instead of equal. And that's somehow easier. And it's all he needed because he was just up and down things. So basically the idea here is, I just want to basically explain briefly where this types of sums come from. So the idea is that you can start in the circle method, by decomposing a point count roughly as, some integral over the circle, which I'll abbreviate as, I'll sort of cheat on the integral. You use moduli or denominators in your Fourier fraction, or not your Fourier fraction, but your fraction up to size x of 3/2. So that's a degree over 2. And then, yeah, I'll just replace the integral with the length of the integral, 1 over n times x of 3/2. And so A mod n, sum over, I'll replace the region K with just this like box, I guess. E sub m times A of x. This sum detects whether f of x equals 0 for any given point of x. So this is just the circle method. And then this is something. Okay, so the main point here is that these sum x is shorter than x of 3/2. So these exponential sums are sort of incomplete exponential sums. But like Poisson summation allows you to write it in a dual form that is shorter. So basically, the key thing is to think of this length. The length divided by how long the actual sum is the complexity of how complex your incomplete exponential sum is.
Perhaps you should say one word that, of course, it never have major and minor arcs. There are no minor arcs and major arcs. You can't afford that at this level.
Yeah, so we're giving a uniform treatment over the whole circle, which is why it's, I guess, this in this lie, I'm sort of pretending this integral doesn't exist.
We can do that actually. I noticed that Maynard was doing that in his lectures, remember?
Oh.
He did exactly that.
Okay, so maybe if you haven't seen this, so SCN is sort of a complete exponential sum now, but we add a Fourier transform, the SCN. And maybe, I guess, regarding this complexity, an analogy is sort of, there are these movies where the car is traveling so fast, the wheels look like they're going backwards. And basically the point is that, the camera only has so many frames per second, so it can only capture phenomena that are so complex. So the point is that this complexity, we need enough sampling in order to recover the original exponential sums. But it boils down rigorously to just Poisson summation. Okay, and then if you sort of, n over x is kind of like at most x of 1/2. So then if you sort of look at this, it's sort of basically what I wrote earlier. Yeah, so let me call this double average like star, because I will refer to it, so I can refer to it later. So then this thing is basically okay. Okay, so let's see. So now we've sort of reduced things to studying these exponential sums are average on average. So basically, since we want to do estimates, it'll be convenient to normalize the sums. So let SC tilde n be, I mean, it's sort of a 7 variable sum. And then so we'll normalize it by n to the 7 halves. And then this is, it turns out that maybe it's not too surprising, but basically these exponential sums are related to the geometry of these hyperplane sections. So I'll let VC be the sort of cutout and projective space, so in 6 variables, so P5. By I mean, not just f equals 0, but also we're looking at these hyperplane sections. And then sort of a basic thing we want to, I mean, in order to say anything, basic fact is just that there exists a discriminant polynomial that measures the singularities of this hyperplane section. So for example, this discriminant polynomial will vanish if and only if the variety is singular. And then, unfortunately, I don't have too much time to explain this, but let me just summarize the results. So basically, the key lemma due to Hooley is, so if we look at a non-singular hyperplane section, then these exponential sums look to first order the coefficients mu z of n of, so it's not going to be an L function, but 1 over an L function. So I'll sort of briefly explain what this is. Hereby, I guess we're looking at sort of the so look at the variety over. Okay, so I'll just, I don't have time to say too much, but I'll at least hint at where this 1 over L arises from. So the keys to the lemma are that, so one important thing is that F is homogeneous. If F were not, then the SCs would not even be multiplicative, so there's no hope that they're related to some L function. And then another thing is that, I mean, this VC is, it's isomorphic to a hypersurface. Since we're slicing by VCs, we're slicing by a linear thing, so it's just like a hypersurface of dimension groups. So yeah, so it's a cubic threefold, and because this dimension is odd, when you apply the Lefschetz trace formula to count points, mod p and so on, you'll get like there's a -1 to the h. The h3 term has a minus sign, right? So that's why there's a 1 over L function and not an L function. Okay, so a sort of, I mean, just explain, I guess, the idea behind Hooley's work. is what he called sort of the two or double close to method. Yeah, this is the two I mentioned earlier. So, yeah, the idea is I guess we can sort of make some. I guess basically the way I'll phrase it is assume for simplicity that this like every C gives you a sort of non-singular. And I said these exponential sums are sort of only related to first order phi, like Mobius type coefficients in UCI. But let's say they're actually equal always. And also, let's say that assume like some elementary form of GRH, right? So that these coefficients cancel the square root. So sorry, I'm gonna have to. So this implies that this exponential sum that the key sum in the like delta method is less than x to the 3 plus epsilon. And the reason it's called the double closed-loop method is sort of because there are sort of like in the circle method, there's kind of both numerators and denominators, and we're averaging over both the numerators and the Okay, so I guess in the last 10 minutes or so, I'll try to explain what is new. Okay, so the point is to assume standard conjectures so it turns out for technical reasons, I need maybe a few more L functions than deleted, but certainly the, let me just write the plan first. Maybe exterior square and then. Okay, so the point is Hooley sort of went to the line 1/2 plus epsilon, but if you want to go to the line 1/2, then you need to study also these second order kind of L functions. But somehow the most important one is still this one, the same one. So for simplicity, let me just say hypothesis HW2, which is kind of an obvious generalization of hypothesis HW that Hooley had involving these extra L functions. And then the sort of most important thing is going to be I said there are these random matrix theory predictions that's precisely the ratios conjecture that I'll explain. And then another thing is, I guess, let me call it Krasner's lemma. So let me just, this is like a technical thing, so let me just briefly say what it is. So basically I want an effective version of Kissin's thesis, which is called like local constancy and p-adic families of Galois distributions. Basically, if you want to actually use, like, basically you need the L functions, their local factors that only depend, like, to be controlled when you vary C. But it's like a purely local thing. Okay, and then I guess so the square-free sieve conjecture, I sort of already said what that kind of is. It's related to these p squared, the p squared dividing the discriminant d of unlikely event. So weird. So assuming these hypotheses, then are all nice. Okay. satisfying a technical hypothesis not really important for application to sum of two cubes. But it could probably also be removed with enough work. Anyways, then okay, I'll state this in sort of two parts for then okay, this party little one up to a constant holds, but also in fact this party little one Hooley conjecture, when you add in the like party little part, the random part, and the structured part, this also holds. The reason I mean, of course, this one implies this, but somehow I can prove this under slightly weaker hypotheses than this. That's why I mentioned it. Okay. Okay. Let's see. So let me say what the main thing to explain is what the ratios conjectures are. So what they do is they give you predictions of random matrix theory type for mean values over LS over family subsets. So a family, for example, is this C up to x to the 1/2. It's sort of there in C. And then here, of course, we restrict to the discriminant is non-zero, because otherwise the alpha, we need a smooth variety to define the Hessian alpha. Okay, so yeah, okay, so maybe I'm a bit short on time, so let me just like maybe I'll sketch like two of my favorite ingredients, I guess. So proof ingredients. So they include what I'll call R2 prime and a and let's say partial results toward a dichotomy conjecture. Dichotomy conjecture over finite fields. So I guess I'll just try to state these two R2 prime and the dichotomy conjecture and then finish. Okay, so I'll state the dichotomy conjecture first. Maybe it's a bit simpler. So the point is maybe if T is a large prime, and I look at a tuple such that randomness fails for the number of points. So skirt cancellation fails badly, I guess. Then basically VC has to contain a plane or something like that. So let me just write this as then, for example, you'll have to have something like this. So yeah, this conjecture is saying like giving you a precise randomness structure dichotomy for cubic free flows of reflection. And then so I'll finish by stating the random matrix theory, or one of them at least, the one that's simpler to explain. Okay. basically this will not be the ratio conjecture itself, but it will be an application of the ratio conjecture. So let's see. For certain holomorphic functions, for example, just think of f of s equals to f squared. The average of C the same family that I was explaining earlier, but we'll restrict, of course, the discriminant non-zero. And then you look at this integral. It will be, I mean, not just whenever L, but I guess it will be slightly modified, since this is kind of what naturally arises in the applications. So we're looking at sort of close to line 1/2, and then there are these things near the line 1 that intervene. Integrate to make this make sense. So, I mean, if you just apply GRH, then there would be like an epsilon here. But somehow, the point is that there should not be an epsilon here. And the point is, like, if you look at a different family, there might be a log here because, so the fact that it no longer depends on the symmetry type of the family. And yeah, okay, so this is for like. Yeah, so okay, so well, I mean, I guess let me just mention some people that are involved in the proof of these, that I quote a lot of people, I guess. So sort of some of the people are this is all 90s. So they proved like sort of general useful worst case type results, and then also needed some more recent stuff. For example, work with Lindner around I mean, the last few years, which sort of takes into account the types of singularities in a variety, not just like the dimension of this singularity. Okay, and then for this random matrix theory, there's of course a lot of people, for example, Montgomery, I'm skipping a lot of people, but Sarnak, yeah, but I guess Henry Farmer's zero power argumentations conjecture, which is the most direct application. Okay, so yeah, I'll stop there. Thanks very much.
Are there any questions for Victor?
So what you're really proving is for orthogonal polynomial, cubic in 6 variables, count the number of points in a box, and capture via this, what we call it, the double Postman method. You can capture the trivial solution from the harmonic analysis. That's your method. That's what you do that. It's quite remarkable because the general conjectures, once you get to the variety that, I don't believe that. And even the person who made it, Bulgaria, maybe Langlands. And that is that most points, the irrational points, lie on subvarieties, and otherwise the randomness takes over. And so this is an example of that where the special points are diagonals. You're picking them up from the Postman method and going beyond that. That's really the way I would explain it. It's quite more. Pick up the diagonals, or the special subvarieties. That's this kind of problem.
Yeah, I guess I didn't get to explain that. Yeah, I guess I did.
I might point out these works consist of 400 pages. So, 10 minutes, not going to cover it.
What is this Square-free Conjecture?
Okay, so basically, yeah, okay, I can speak that. So basically, we expect the probability if we look at like C in some box, tuple C in some box, then the probability that there exists a large prime squared divisor. Let's say P is around size P, capital P. This should be like at most P to the, that this probability should be small, like some power. And it's known in the function field case by Langlands.
If somebody's asked you, in the function field, what is that?
I think
There's a lot of all the Riemann hypothesis and the modularity of it.
yeah, so it's there is some technicalities in the dictionary between functions, because basically the problem is that the problem is you need actually more functions than just more L functions than the ones we introduced. So basically, the problem is that an L function in the function field case, it loses a lot of information. Like there's a lot of cancellation about, or like I mean, the only coefficients you remember are like powers of Q. Right? Whereas in a number field, you remember all the. So
Can
there's
I
a lot of
ask,
technicalities, but I think I would expect that basically, based on conversations with Brown, I mean, we haven't really looked at it, but I would expect that you can reduce everything to random matrix predictions.
Can I ask, maybe I missed it, but what is the symmetry type of the L function?
For example, we pick up a Hesse principle from the circle method, from the first one. All the examples I have inputted. Default structure.
Wait, sorry, you mean pick up the Brown model?
What's remarkable here is picking up the diagonal, the expression subvarieties in 6 variables. If you get a few variables, like a cubic, as you pointed out,
Yeah, if you
surface, there's the Hooley prediction can't be correct because maybe it has a failure or some Brownian obstruction. So the question is, with any harmonic analysis method to pick up a Brownian obstruction? I'm just asking if you've seen any such examples.
there's I think some example worked out by a student of Keith Brown a few years ago, Lindqvist. Anyways, but basically there's some examples for like it's for a quadratic actually. Like you can ask questions like strong approximation on affine cone or something like that. So somehow even though weak approximation holds rationally, somehow when you like remove the modding out by scale, there's some asymmetry between the different residue classes. So that can be picked up by the but that so Heath Brown like I guess he cryptically mentioned this to me, but he suggested that like a clue in the circle method can be found in this circle. I don't know how far it can go.
Can I ask a question? I don't know if the people who are not inside.
There's a question on Zoom, but it's
Can
very
Zoom-
quiet.
Turn this up,
Oh,
maybe. Turn it off. Can you ask your question again?
I'll try. So I have 2 questions. First, what is the symmetry type of L functions for which you are applying ratios conjecture? And second question is it the case that in the work of Sarnak and Ghosh, they used, in some sense, a proved version of ratios conjecture?
Okay, so the first question is the symmetry type is orthogonal, so it's sort of analogous to the situation for elliptic curves. The second question, no, the thing is they could sort of, because if you fix one of the variables in the Markov type equation, it becomes quadratic. So you can sort of do things unconditionally by choosing the right regions. When you produce points, you can choose what region to work with. You don't have to work with the hardest regions. You can work with the easiest regions. So they sort of make one of the variables small, and that allows them to do it unconditionally. Unconditionally, but like using like old results on this circle method for quadratic.
Are there any more questions or remarks or anything, including on Zoom? No, if not, then let's thank Victor one more time.